Okay. You're on tape, so she wants your conversation recorded. So we talked a lot about kind of applications in the general kind of intuitive feel of the Fourier expansion, right, last time. Now let's just go through a 50% duty cycle square wave, right? Because this is what is a major part of your project in 110 lab. So now we're getting into it. All right. And so over here, A naught, right, we are taking the average of a repeating 50% unit square wave. Unit means it goes from 0 to 1. And notice we go from 0 to the period and we divide by the period. And that just means we're just taking the average. And, you know, if you think about it, let's just take it, just settle our minds, right? That if, if I sum these up, right, you know, I get a sum. But for an average, you get your sum divided by the number of averages, the number of samples, right? And so if we recall, because sometimes you can really get into the you know, the integration table or whatever, and you can kind of one can, not you. We all can. All right. That if I'm like, what is it that integration, you know, really is, right? Is that we're taking slices, right? I'm trying to draw them evenly spaced, right? And we have little areas, right? And we're summing them. Get a better sum symbol. And yeah, the width of the slice, right, goes to 1 over infinity, right? And when you start to take the limit of that, well, all of a sudden we have integration, right? And sometimes it's just helpful to remember um, that you're just summing little slices, and the slices get smaller and smaller. So now, you know, let's say I do this, and this repeats. Right? I'm not going to show it repeating. Well, rather than divide it by the number of slices, right, we divide it by the period, right, and we just integrate. I'm just calling it f1 of t dt from 0 to t naught. And that is just the average. All right. So let's come back to the example at hand. Right, this is time. This is 0, 1. And right here, this t naught divided by 2. Maybe I didn't draw it perfectly. All right. But off of the top of your head, what's the average of that? 0.5. Okay? So somebody else, answer this, please. It's on for 3/4 of the time. What's the average?
27.
27. Okay. Yeah. All right. And, not to scale, but it's 1/4 of the period. Somebody else, what's the average there? Yeah, 0.25. So now looking at this shape, is the average going to be 0? Nope. Yeah, so the answer is no, because it's always positive. So the average has to be positive, right? So now I'm just going to call this, 2. We'll call that like 1, right? And use red, all right? So the thing is, we can kind of come up with an average. It might not be completely accurate, just by drawing some boxes, okay? So again, I'm going to draw one box here, and I'm just guessing, all right? And I'm going to say, I'm just going to call it a half, all right, of the thing, right? And I can draw a trapezoid here, again, not perfectly to scale. And then I can draw a triangle here, right? And so I have area 1 equals, a half of the period times 1, right? Area 2, I've really drawn that. I've drawn it too far off. I'm sorry to do this to you. This is 1/3 and 2/3. All right. So area 1 is 1/3 times 1. Now, what's the distance here? 1/3. Because that's actually, so that distance is 1/3. The height is 1 plus 2 divided by 2. And then the area of 3 is 1/2 because it's a triangle, right? The height is 2 and the base is 1/3. All right. And so, yeah, I mean, that you could say, well, that's Calc 1, right? Or it was algebra because what did we do? Or geometry, right? The area of a rectangle, the area of a trapezoid, and the area of a triangle, right? And you can estimate these things, pretty well. We're all estimating these pretty well just for looking at it, all right? And, oops. Now the thing is, let's just draw your attention. The equation for A0 is 1 over the period, right? It's just average, right? Now now I haven't drawn it very well, but what do you think the average of this is? Yeah, my intention was 0, right? You know me by now, right? That's 0. Now, does this look at all familiar to you? Hmm? You got to speak up. Yeah, the RMS equation, right? Except, what's RMS of a sine wave? Listen, just shout it out because you know it. You just lost your confidence. What is RMS of a sine wave? Square root of 2 over square root of 2 over what? Yeah. Or what? 0.707? Yeah. Okay. Even I can remember that. So this looks like to RMS, except this average is 0. What is missing? Hmm? Squared. And now that I've squared it, I've changed the units. So what do I got? Naomi's nodding. No, this was nodding like, oh yeah, I totally get this. So what's missing now? You know it. Just say it. All right. Anybody else? Right? What I'm going to call it RMS. I have all of this. This is squared. So if I'm doing voltage, right, now I have square volts. But the units, you can't change it, right? So what do I have to do? Okay. So I'm interpreting the symbol that Naomi made, which was the square root. Yeah. Okay. So I say that sometimes I'll say something like, remember you learned this in 98, and people take it to mean in a different tone of voice, you should have known this already from 98. No. This should help you. You've seen this before, and what you learned before will help you learn this. Okay? No bad intent, right? Because think about it. RMS takes something with frequency, right, and turns it into a constant, right? This had frequency and it's turning it into a constant, right? All of these had were frequency dependent and we're turning it into a constant. Okay? And so I'll start deleting things. So, where are we headed in all this, right? Is we're going to have A0, which is a DC value, it's a constant, plus we're going to sum up AN's cosine 2 pi f t, right, n equals 1 to infinity. So we're going to be finding these constants, but where does the frequency come back in? Is because we're finding these average values that when multiplied by the correct cosine, and I'll just put the bn. I'm just going to put the sign. Da, 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 da. All right. So you really have to know what the period is, and we'll be finding these constants and these constants, right, and this constant. But we've already, without math, per se. We have already intuitively found what the DC offset is. And so to kind of bring it home to what you've seen even more, right? Okay. So that's time. I'm going to call that 1 to 0, right? So A naught, right? What's the DC offset of that? Yeah, 0.5, right? Because if I subtract 0.5, I'm doing 0.5 to minus 0.5, right? So A naught is just 0.5. And then how many, all right, assume this is a perfectly drawn sine wave. Okay. How many sine waves are there? Oh, I'm sorry. How many sine waves are here? Not periods, just how many are there? One, right? So um, and since it starts at 0, right? Or hmm, I've drawn it a bit funny. I have one sine wave, and the amplitude, right, is 0.5. Right? Now, yeah, if you saw something like this, you'd think, no, I'm not drawing that right. You might think there's two, because you can kind of see something going at one frequency and something going at another. Okay. Um, but there's A naught and there's B1. Okay. Now I have drawn this a bit funny, but from an intuitive standpoint, okay, we've done it. So let's go back here. So here's A naught, and we're just taking the average, right? And so it's 0.5. And you can see that, yeah, I set it up from 0 to half the period, it's 1. And then 0, half the period to the full period is 0, and you get a half, right? And the reason why I mention this in RMS is that is that if you had 98 and used my open math, there's questions there that have shapes like this, and you break them up like that, right? So that you can get it done uh, more easily. Like you transform the problem so that it's just easier to deal with. And so you might need that skill set here. All right. All right. Now, A naught. now we're taking twice the average, but now it's xt. I've been using ft prior, but it's xt times cosine, and then n. It's not. It's 1, 2. Conceivably, it's 1, 2, 3, 4, 5, infinity. We don't know. All right. So we go through. So for half the period, the function is 1, right? And in the other half, it's 0, so you can ignore the other half, right? So 1 times cosine, we take the integration, and we get that no matter what n is, an is 0, right? And that's because the square wave, as I've drawn it, yeah, it's an odd function. So odd functions don't have cosines in them because cosine is even, sine is odd. So just by looking at it, one could have said, oh, there's no cosines in there, therefore it's all odd. All right, so then we come here. Now we do the b's, but now we're integrating sine, right? And we get cosine n pi minus cosine 0. And what we find is that the evens drop out, but odd numbers work. And that the coefficients are 2 divided by n pi. All right. And then if you go using the C notation, there's a phase. All right. But if you sum up these, you think, well, let's get back our square wave. Okay. So that's the full-blown mathematical way. But on an exam, which I'm thinking is like a job interview, what's this? The way I'm puzzling it, that's how you probably should go. Unless, some people, they like to give exams for job interviews. You sit down and I don't know. I think they should just hire you. My opinion. You guys are great. So what I've done here is programmed everything. So A naught is a half, and then I have the frequencies, 1 hertz, and then 1, 3, 5, 7, 9, 11, 13, right? And then the scaling constants, 2, 2/3, 2/5, 2/7, 2/11, and 2/13. And then I just put it in here, right? And let's see if that's still, yeah, drop. Okay. Dropbox. Anyway, it's there and you can download it. You just have to click something. Okay. So now let's see how this progresses. So V of A naught is a half, right? Which is a pretty poor approximation of a square wave. But, and the thing is, though, is the average error, if you will, would be 0, right? Because half the time it's too high and half the time it's too low. But as we know, when doing a root mean square error, you have to square the errors and add them up, right? Well, now we add our sine wave of B1. So now it's up. Now this is, right, a square wave, it goes up to 1, comes over back to 0. So there's a lot of error there, right? But it's minimizing. And you can see we keep adding it, and it gets closer and closer to the square wave to where we go up to 13. Okay. And has anybody seen this before? Okay. If I were able to do this, if I had the time, right, and I took this out to 100, or 101, I should say, what's going to happen to that? That's the final square wave. Do I ever get the square wave? No. All right. Now, actually, you did do this in lab, right? Um, so I should have heard a chorus of no's. And yeah, there were people who would take all the function generators in lab and try to hook and set it to each one and sum it up and say, well, it's digital. There's an error there, right? But no, you can approach it, but there's always going to be that error. And it's something like, yes, when you take the limit, they're equivalent, but there's this energy that kind of leaks out. Now, yeah, if you put a low pass filter on that, you get pretty much your square wave back. But the thing is a real square wave has infinite slope on the way up and down. Well, you can't do that anyway. But you can see, those harmonics, right? So let's come back to the motorcycle power system, right? Now this was, I don't know, what's the RPM? Well, it changes, doesn't it? No, it's the electric motorcycle, right, Joe? Oh, all right. So anyway, the frequency to DC to AC, the frequency will stay the same, right? So let's say, it's a kilohertz. So that means, yeah, you have the DC offset, if you'll have some DC offset, let's say it was a square wave, right? And you have all these harmonics, right? Uh, I'm just, no, I'm not. I'm just saying, if this was a kilohertz, right, that'd be 3, 5, 7, right, and so on. And so these high frequencies are there, right? Those harmonics, and that's what they look like, are there. Okay. Oh, sorry. Yeah, so the question is taking the Fourier expansion and then summing it up in time, right? Which is like a digitization, right? Except now you're digitized in frequency. Even though yes, LT Spice is digital, right? But it's approximating an analog system, right? So even if we were using old school analog function generators, right? This would still happen. Um, but it's the steps that are, it's the actual analog voltage or the signal that's being broken up in the analog to digital converter. Okay. This is, you're somewhat digitizing the frequency because we're not doing infinite frequency. But even if we did, like, it's a mathematical thing. When you take the limit, oh, then it's equivalent. But when you sum them up, right, that energy term is there. So those high frequencies are there. And, a quick break from the math, all right, is that we have a digital IC output driver. And so you know what I mean. Just pick one. So over here, you see these packages, and these have wire, like a leg, right? And that at certain frequencies, you'll notice the the inductance and the resistance, and then there's a capacitance. And sure, you can have quad flat packs that have less of this lag, but what they're not showing you is the inside of the chip and the wires that are used to connect things. Now there's ball grid arrays and it can be minimized. And actually, for those of you in 153, you might have seen that last week, depending on who your TA was and what microscope you had access to. All right. But you have an inductor, you have a parallel capacitance, and then you have a resistance. All right. And you can find, if I'm driving it, so this is the inside of the chip, the driver, and no, this is coming from the outside, and that's the pad. So you're driving into the chip. And so you just, hey, those are linear elements. You know what they are, right? You find HS, H of S, and notice we get a second order function, right? If the 1 over LC wasn't there and it was just S squared, what would we have? High pass. And if the S squared was missing, what would we have? Low pass. We have both together, we actually have a notch. And here's the Bode plot. And at this particular frequency, right, it's blocking. All right. And so you might say, well, wait, my chip pin speed is 10, 20, 30, 40, is 50 megahertz. Hey, that's well away from here, right? Or let's just say 10 megahertz, right? But no, where's 100? 10, no, 100's right here. Let's say it's 100, right? Well, going up just 10 harmonics puts you right into that range, because digital signals, right, from 118, right, are square looking, right? There. Now you've studied for 118. And so those harmonics, which are needed to get the full digital signal, right? Because think about it. That could be a digital signal, right? It's just you could interpret anything above 0.5 as 1, anything below is 0. So you could get data out of that. But again, with all the noise and you would need like a Schmidt trigger, right? You would want, the better the square wave, the better your logic levels are going to be, right? The less errors. And now we have something blocking it. So seventh harmonic occurs when n equals 13. And now what I'm trying to do is just show you the seventh harmonic needs to be below 1 to 2 gigahertz. All right, that means my maximum frequency is about 153, right? And yeah, some pads will go up to 130 megahertz. So that looks pretty good, right? But this is 50 megahertz, looks very square. Even 70 megahertz looks pretty square. 80, all right, there's a little something going on here, but it's still digital, right? 100, 130, 160, 500 megahertz, we're starting to see 20 gigahertz, right? What? You know, that's pretty hard to interpret, okay? Now, um, that's a bit of what they like to call a toy example, but you can see that the bonding wires and getting the data in and out of the chip does affect how fast you can get data out of the chip, but I would be remiss in my duties. There's a couple of things. Is that, let's just say there's a logic gate. Now I'm driving it the other way. So power in an inverter is alpha C load VDD squared times the frequency. All right. Now this isn't on the exam, but I'm just saying, if you have a 50% duty cycle, right, every time, or if it's switching every clock cycle, alpha equals 1. What's the average of how much you switch? All right. C load is like this, and off chip it's big, right? We're talking about a driver. Then VDD squared, well, now it's something. And then here's our frequency. So not only if you go too fast, the signal will get warped, but the power dissipating, right? And let's just say here's the ASIC and here's my inverter driving the pin, will get really hot to the point where no matter what kind of gaming cooling device you have, you're going to melt your CPU, right? And yeah, it's like, oh man, I can get 20% by overclocking. Yep, you sure can for a certain amount of time. And if that game is really important and you only need a few hours to be able to play that game before your CPU blows up, okay, it was worth it. Intel certainly thinks it is, right? So I just want to give you the full picture, right? But in like 110, it's more like we're warping the signal, right? 118, everything is still pretty ideal, right? Then as you go farther and farther along your career, they merge, right? And you get the full picture. But if I know a big Silicon Valley, it lives and dies on this equation, okay? And that this is for CMOS. Other logic styles that were faster just burn power kind of for looking at them. But with alpha, if you turn off a part of the CPU and set it to 0, well, then there is no power. So you can have things that are power aware. All right, but if you're not able to manage the power, you really can't integrate the circuit, okay? But that is the true driver of Silicon Valley, not social media. Okay. So that is with the square wave, right? That started us looking at, hey, what's the average? What's the DC? Which we can do by eye. And then we can even do by breaking it up into rectangles and trapezoids and triangles, right? And then you sum up the areas and then divide by the period, right? Now we have a knot. But the task there is you need to be able to identify the period, right? It's a sine wave. What's the period of that? We talked about how we're creating this Fourier expansion, but we're really coming up with averages that then, which come up with constants that when we multiply it by a cosine or a sine, that's how we get our original function back. Okay. And we just did like another one by I, and we talked about the pad example. Okay. Any questions so far?
Fourier coefficient is the average, uh, I guess like DC average of the signal at the frequency of that sine wave. Like if you're adding
DC, well, what it is this is an average, right? And I never thought of it that way because I don't like to muddy the waters. But yeah, it is. I'm just going to use xt and then cosine 2 pi n frequency t. So dt. So this is a DC, that constant is a DC average of the function times the particular 2 pi n times the particular frequency of a, so the particular cosine that you're interested in. And again, the BNs, you're finding this average. Okay. So this is, that's an average, and this is an average. I don't use the phrase DC, even though an average is like DC, right? And so when you say DC average, it's almost like saying more than you need. But the reason why I say it, you know, for A0 is like it's the DC part or average. And I'm just trying to link the concept of DC to that. It's just the DC is just the average. And I might start speaking so fast that I say DC average, right? But yeah, those are all constants, right? Um, if the thing repeats forever and ever. Uh, the easy answer is you're going to get 1/2 the right answer if you don't have it there. The, the other part is, and I have to, there's another way of looking at it where you split the function like this and the period is and that the 2 isn't there. So you might see this is right the way I've shown it, but there's other things where that 2 won't be there, right? Um, yeah, it doesn't make sense. Like the average is the average, but you won't. Um, maybe it's the amplitude. You just have to multiply it by 2. But yeah, it won't work. I've tried. Yeah. The question is why is there a 2 there? If it's twice the average, the way we described it, right? And I'm saying it in this context, you need the 2. There's other formulations where you don't. Okay, maybe even 112.
is there some symmetry in the expected symmetry? Because if so, that two might be like a shifting the limits of integration. Instead of going from negative T0 to T0.
Like I have what it is I have to go find the other way to do it. Which I found was less intuitive. But sometimes it's easier. Like you can have a triangle. Like if you were able to shift it so that you could get an odd or an even function, right? So here's the thing, right? That would be t0 divided by half minus t0 plus. Now the way I've just shifted this in time. Well, now it's an even function, you see, and so maybe it would be easier to go that way. But that's not. I got to look it up, guys. You know, great question. But what do they use in 112? Yeah, okay. Yeah, so minus pi to pi, they're doing it the other way. So he might that might, anyway. Um, I did change the assignments. Now everything is, you know, controls and Fourier are all due on the same day, right? I figure you can figure out what you need to get done in your time, right? Just checking to see if I have any my open math ones. So by hand. Okay, should be able to read that. Okay, the DC average, or the DC part, or the average, right? What's A naught? Zero. Uh, what's A naught? Yeah. What's A naught? It looks like 0.5. Sure. Right. And then we did examples already of that. Now, yeah, the period, right? The periods here are the same. But notice I've taken that signal and squared it, and the frequency doubled, right? So that's just like in the RMS problem when you have you take a sine wave, pass it through a bridge full wave rectifier, and now you've got it doubles the frequency, and that comes right out of the. Um, I mean, there's a trig identity for that, right? Okay. kind of filter. Just want to double check that. So this is a 50% duty cycle square wave, except now it's 100 kilohertz, right? And we can plot this out, except it's a linear scale now because we have zero. So A naught is like at zero frequencies, right? And that's 0.5. So that's zero, right? And now I don't have enough space to write out the whole frequency, right, on the axis, but that is 100K F3 equals 300 kilohertz, F5 equals 500 kilohertz. So when n is 1, you get 2 divided by pi, and it's a little bit higher. Okay? But then you're going to see this drop off. And so this would be 2/5 pi. This would be 2/3 pi, and this value would be 2 pi. Right? So that square wave causes these harmonics, and they go on for infinity. Right? So we've seen something else, right, with the frequency axis, except it's a logarithmic axis, right? We've seen low pass, and I'm just not going to draw the axis. Okay. We've seen high. We've seen band, and today we did see notch. Okay. Notch. And think about it. The amplitude is multiplied by this number up to a point, and then that number decreases with frequency, low pass. Here, it's attenuating low frequencies, because remember, these are all sine waves, right, that are multiplied by the attenuation constant, and that's our output. Here, it's kind of like 0, and then it passes one frequency, and here it blocks one. All right. So the question is, if I wanted a DC signal, I only want the DC. Which one would I use? Low, high, band, notch. Low, right? And I'm going to try to keep the, let's see, what's that? That's blue. So again, what I'm drawing here is not strictly kind of legal, because this is a Bode plot with a logarithmic scale, right? And this is the Fourier spectrum on a linear scale. But I can tell that you want to keep that. All right. So now I want a frequency, I want a sine wave of, so I want, oh, no, let's say, now I want to block DC for some reason. It does happen. What kind would I use? High pass. Okay. Because it's blocking the DC somewhat, right, and passing all of those. Now, what if I want only 100 hertz sine wave? Which one would I use? Band. What, 100 kilohertz? Right? Huh? Without dividing it and all that? No. You would need tricks. Okay. What if I wanted 500? Only wanted 500. Okay. What if I want to get rid of 300? Okay. So that's it. Okay. So now, let's see if I can do a quick example. Okay. What's A naught? 4 and change, right? Um, interesting. Something interesting, right? How many frequencies are there, roughly? I mean, the correct answer is infinity, but notice I've got this longer shape and then a smaller shape that then turns off, right? It's really quite weird, right? So, but what I'll tell you is things with discontinuities like triangle, square wave, they have infinite harmonics. So let's just take a look. Okay. Um, which there's so many frequencies, it's really hard to tell. So I'm going to go to linear. And even still, and what I need to do is change the simulation like I did last time, which I think is, I wanted to go, let's go 10 and start saving at 5. And let's run this one more time. Oh, I screwed up. Saved it at 5 nanoseconds, not 5. Now, what I want to do, like last time, we did a convolution example. I can walk you through another exam problem. But we also have this topic again on Wednesday. That's enough of that. All right. So I see something at 10 and all of that. So if I want to get rid of those harmonics, right? What kind of filter? Hmm? Low pass. Where do you think it should be? 10 megahertz, 1 kilohertz? Where should I start attenuating? Hmm? Yeah. I mean, the thing is if I if I make the band, if I set it here, right? Well, the roll off of the filter isn't that great at that point, so it's not really going to attenuate that. But this is what this is 40 dB above the signal, so I would want to make sure that wherever, so a first order filter, right? So that's 13 kilohertz. So if I go to 1.3, so if I go to 1.3, right, and it goes down by 20 dB per decade, by the time it gets to here, right, that that extra 40 is now to 20, but it's still higher. Well, if I set it here and make it second order, it drops off by 40 dB per decade. And so now that plus is now even. So, right, I just might have to put it way out here with a second order filter to where it's attenuating by 80, right? Because 80 gives me my 40 and then pushes it down another 40, right? And so, that's a rough idea how that. Okay. Now this one was during the sample, right? And we want to match 4 impulse responses, right, to 4 outputs. All right. And so, but in this case, it's not a step function, right? The input is a sine wave. Okay. But that sine wave, right, it's the same. Is there a DC offset in that sine wave? No? It goes from 0 to 1. It never goes negative. Is there a DC offset? Yeah. Okay. So now you didn't really need to know this at the time, but yeah, that means A naught is, I probably said 0.5. All right. So there's a DC signal there, right? Now, if I look at A, so low pass filters, what do they do to DC signals? Pass it, right? Because it's the ultimate low frequency. So I'm looking at A. Does it look like it's passing a DC signal, the blue? Yeah. Now, what about B? Is that passing the DC? Yeah, I think it is because not only that, but it's passing the frequency it's almost passing the signal itself, right? Now, when I wrote the question, I made sure that it attenuated it a little bit so that you could see the difference between the the blue and the green lines, right? Because if I made it perfectly pass, they would have been one over the top, right? So the filter, right, it's low pass, but the cutoff frequency is just below whatever is going on here, right? So this one's passing a higher, it's a low pass because it's DC, but it's passing a higher frequency. And this one is kind of blocking that. Notice it's really attenuating that frequency. So the cutoff frequency for A is lower than the cutoff frequency for B, which means the time constant is bigger for A than B, and they're both low pass. Now, same signal. And again, it takes time to get to where you're going, right? So you can evaluate it there. But the blue line, oh, I guess I called everything A and B. Oh. Anyway, is the blue line have any DC to it after 6 seconds? No, right? And what about in time response D? Right. No. But notice the amplitude is bigger, right? So it's passing more of it. That means the cutoff frequency is like lower. That means the time constant is smaller. No, the time constant is bigger. And then here, right, it's attenuating. So the cutoff frequency for this is higher than the cutoff frequency for that. And so that means the time constant for this has to be smaller than the time constant for that. And without anything, you can then just go for it. Okay. What I found is people were getting confused about higher and lower frequencies and things like that. Oh, I can't draw it on the board as we're recording. All right. So you know, like it was actually they would memorize, they would have things backwards, but that frequency is lower than this frequency. This amplitude is bigger than that amplitude. All right. Um, but think about it. Why, all right, can anybody hazard a guess as to why I like to show the picture? Or I ask you questions based on a picture.
Because that's what we're gonna see. So,
Thank you. Yes, that's what you're going to see on the oscilloscope. All right. Now, yeah, in the remaining 3 minutes, I can, it's time for the thought bubble where I trash AI. So think about it. You guys all recognize a sine wave now. What is the period? What is that? You do it intuitively. And now, yeah, we can use the FFT to determine what everything is. It's a mathematical tool, right? So I bought this book, and it was about AI and small microcontrollers. And the example was really detecting a sine wave. Now, there are so many better ways to detect a sine wave than AI, but the reason why they chose that is, well, you already know the answer. So if you're trying to follow along and it doesn't detect a sine wave, it's your programming, right? Or you didn't do the constants right. But the other thing is, like, with that perceptron, we have all these inputs and then you have the output, right? Well, the thing is an inexperienced person will put all the inputs they can think of into their network and then let it train, right? Which then raises the global temperature by whatever, all right? So the thing is if you knew detecting sine waves, you could probably prune, I think the term is, like, you can prune, all right, that one isn't going to impact, that one isn't going to impact, and you could come up with a better model, right? Because you knew what you were doing, all right? Now, I just want to. So the poster is more towards the EE office, but that's a poster of students who used AI to design circuits. All right, it was pretty cool. Um, but they weren't able to do it until they actually had some 118 knowledge. I threw them into it because they really were dying and they didn't want to do analog because they haven't had 98 yet. But they were able to use schematic capture and NOR, things like that. But when it came time to use ChatGPT to design some Verilog code, they hit the wall, and I had to find somebody to teach it to them. Then they were able to use the ChatGPT to refine the prompt and all of that. So you know, let's see, what were you guys doing? I think you had 4 states, and some states went like this, and some states went like that. Okay, right? But can you? And so the thing is you can do that in Verilog, right? Why learn a K map, right? Well, that's so that you can understand what the tool is doing, right? And so, um, you could try ChatGPT to come up with those answers, but until you've seen it a few times, you don't know if it's working or not. So, yeah, that was a great thing I walked in on. Have a great day.